Hello, this is Jennifer Martinez. In this section, we're going to talk about matrix operations. Let's start with sum and scalar multiples. First, what I'm going to do is read the first paragraph of this section, which says that the arithmetic for vectors described earlier has a natural extension to matrices. So in past sections, we mainly talked about vectors. I know we did take a matrix times a vector, but there was always a vector involved. In this section, starting in this chapter, we are going to now start talking about adding, multiplying, subtracting two matrices. Therefore, they want to talk about when two matrices are equal. And they say that two matrices are equal if they have the same size and if their corresponding columns are equal, vectors, which amounts to saying that their corresponding entries are equal. And then the next thing here is about adding A and B. Turns out you can only add two matrices if they're exactly the same size. So that's why they have, if A and B are n by n matrices, then the sum of A and B is also an n by n matrix, whose columns are sums of the corresponding columns in A and B. The key thing to note here is the end, that the sum of A and B is defined only when A and B are the same size. So let's look at example 1. So here we have A and B, and we want to add them, and they are the same size. This is 2 rows and 3 columns. This one is 2 rows and 3 columns. So we can add them. You just add the corresponding vectors. You can do that and think of it that way. Or you can add the corresponding entries. So 4 plus 1 is 5, and then -1 plus 3 is 2. That's the first vector, column vector. And the next one you would add 1 and 8, and the last column there would be a 6 and a 9. Notice how you cannot, A plus C, they say, is not defined because it's not the same size. This is a 2 by 2. What about scalar multiplication? Scalar multiplication is taking a scalar, multiplying it by a matrix. Well, I know we've done this for a vector, but now we're doing it for a whole matrix. And by the way, they say that negative A stands for -1 times A. So that would be the same thing. And A minus B, so they were not going to define subtraction because A minus B, as we know, is the same as A plus -1 times B, which is addition. So they give an example here using the same matrices as in example 1. They take 2 times B, and notice how it's 2 times each vector, so it ends up being 2 times each entry. And here's an example of A minus 2B, so then they're going to take, here's the A, the original A, and then they take that 2 times B and they subtract them now. So you get 4 minus 2, and then -7 for -1 minus 6, and they do it for each one, 0 minus 2 and a -7, and the last column 3 and a -12. Here is all the properties. You could prove these pretty easily. A, B, and C, and they do in the book if you want to look at those. A, B, and C are matrices of the same size, and R and S are scalars, right? Addition is commutative. You can add those. Associative. A plus 0 is always A. That makes sense. If you take a scalar times the sum of two matrices, you can distribute it. And the same with the other way around with a matrix with 2 scalars. And it's associative when you have 2 scalars and a matrix. So make sure you know those properties. That's what we're going to use. But we're going to mainly concentrate in this section is on matrix multiplication. As we saw in the last section, you can actually think of matrix multiplication as a composition of mappings. So it says, I'm just going to again read the textbook, when a matrix B multiplies by a vector X, it transforms into a vector or a equation Bx. If this vector is again multiplied by A, right, this is now a Bx would be another vector multiplied by A, you're going to get end up with a vector a bx, and by composition, if we look at the next figure, another way to go is just go straight to there, and that would be a bx. So you can see that our goal is to represent this composition by multiplying by a single matrix, and it's going to be AB. That's the definition, a way to think about matrix multiplication. Here is the actual definition of multiplication. If A is an n by n matrix and B is an n by p. Now it's going to be really important. You are going to only be able, we're going to see this in a few minutes, that you can only multiply A by times B together if the column in your first matrix is the same as your rows in your second. And they, B is going to have columns B1, B2, all the way to BP. That makes sense. Then the product of A times B is going to be, the result is going to be the outer, the M. Let me just mark that. That's where the M cross P comes from. M rows, P columns. And it's going to look like this. So you're going to take A, B, we're going to write like we've done before as vectors, and then we're going to multiply A by each one of those, and we're going to have a result. Let's do that here. Example 3. We're going to compute AB, where A and B are given here. And so what we're going to do in the solution is we're going to write B as B1, B2, B3, and then compute each. Compute A times B1 using our vector multiplication that we do know about. So this is going to be, the first entry is going to be the first row times the column, so that'll be 8 plus 3 is 11. And the next one is going to be the second entry is going to be the second row in that column, so that'll be 4, and a negative 5 is a negative 1. We're going to do the same thing for each one, A, B2, and that's going to be 0, because we have 6 and negative 6, and 13, 3 plus 10. Finally, let's do A, B3. So we're going to take A times each one of these, and it's going to form our matrix. So what we're going to get here is 12 plus 9 is 21. And then we're going to get a 6 and a negative 15 makes a negative 9. So what is our final answer? So our definition, it's going to be AB1, AB2, AB3. And those are vectors now. Here too. So this is going to be now 11, negative 1, 0, 13, 21, and negative 9. That is what AB is going to equal. Very interesting, because if you note that each column of AB is a linear combination of columns of A using weights from the columns of B. There is a shortcut. Let's go over that. There's a row column rule. So we can define the product of AB as each entry in row I and column J. Before we do this, we should go over some notation. So we have here, if A is an n by n matrix, that is m rows and n columns, the scalar entry in the ith row, jth column is called Aij. Sometimes it's called the ordered pair I, comma j entry of A, and they ask you to look at this figure to the right. So for instance, the 3 by 2 entry would be the entry that's in the third row and the second column. We're used to seeing it this way. Each column of A is a list of m real numbers. It identifies a vector of Rm. They're denoted this way. We've seen this before, but we're observing now that ij is the ith entry from the top and the jth column of vector j. So what this stands for, ABIJ, stands for the ith j entry in AB. So if we want to look for a specific entry in AB, we're going to take that ith row and that jth column and multiply them together and add them up as a linear combination. So let's look at example 5, which is really taking that same A and that same B that we did on example 3. So we can see if we get the same answer. There it is. Example 5 is the same numbers. And we are going to now do this a new way. So a shortcut, as you will. Use the row column rule above to compute 2 entries for AB. An inspection of the numbers involved will make it clear how the 2 methods for calculating AB produce the same matrix. So we're going to just do 2. So they're going to look for the first row, third column. They're going to look for this entry. So they look for the first row, third column. So if you do the linear combination of those, that's 2 times, just like you would do a vector, right? Just doing it all at once. So it would be 12 plus 9, shows right there, which is the 21. I bet we got 21 up here for that. We sure did. And then the second row, second column, so second row, second column would be this row times this column. So it would be 1 times 3 plus -2, 5 times -2. So it would be 3 plus 10, which is the 13, which we got up there as well. So just doing one more example, let's just do that last one. This is the second row, third column. So what am I going to do? I'm going to take my second row and third column. So then I'm going to get 1 times 6 plus -5 times 3, which is 6 plus -15, which is -9. And if you continue to do this, you can check to see that you will get the same answers. So let's just go ahead and check that. If you take the first row times the first column, that would be 8 plus 3. And then the first row times the second column, 6 and -6. And finally, the second row and that first column, let's erase that. Oops. Finally, checking the -1, it would be that second row, first column, so it would be 4 and a -5, which is indeed a -1. So it works. Let's look at example 4. The size of the matrix. I talked about this before, but this really states it here. If A is a 3 by 5 matrix and B is a 5 by 2, then you can multiply them together because the columns of A are the same as the rows of B. What is the definition of A times B? Well, they have here, we don't know what it is, but what are the sizes? So A we know is a 3 by 5. There's what that looks like, a 5 by 2. And these have to match. And the size of it will be the outer, so it'll be a 3 by 2. B times A is not defined. It talks about it here. Because if you took B times A, you would have a 5 by 2 with a 3 by 5, and these inner ones do not match. So ABA is not defined. The last thing in this video is the next theorem, the property of matrices. Matrices are associative. You can distribute One warning though, these are all the rules. You cannot commute